All right, so what we're going to start talking about today is piecewise functions. See, I've got my calculator set up on the other side. I'm not going to use it early, but I will in just a minute. First of all, we need to recognize what a piecewise function is a collection of different functions. As you can see as we look at this one, we have a quadratic equation, and it is being used from negative infinity all the way up to positive 2. And we have an open circle, which means not included, which means this is going to be somewhere else or a no solution. We also have a single point in space, and then we have a linear function, which is just a constant value of -5, which is going forever to positive infinity on the x-axis. So what we're told to do is find f of 2. So what we do is we look across our x value, our x-axis, excuse me, and we are going to see that that's where it is right there, the x value of 2. And from there, we just see the value that goes from there. The open circle indicates, just like we talked about with the parentheses, not included with the data set. And here's another open circle, which means not included with the data set. And a closed circle means that it is. So this is our solution. When f of 2 is what we're looking for, the outcome is the y value, which would be -2. So this is how we evaluate a piecewise function based on its graph. Second example, we're going to kind of try to move these first examples rather quickly. So this again says f of 0. So what we're going to do is look at our function and identify where the 0 is. Well, the 0 on the x-axis is right here, so we just trace our line across the y-axis, and we can see that the solution, the output solution, is a -2. Now, there is no big bold circle, but when we draw a line, we are indicating that is part of the solution set. So my solution is -2. You can see this is two linear functions and then a single point. This is a piecewise function. All right, now get into a little more difficult stuff. What do we do when we do not have a graph? Well, you can do one of two things. You can either put it into the graph, or you can solve these values. What we have here is the functions that you're supposed to use. So this function would be used for the values if the x value is -3. -5 will be the solution if x is equal to -3. And then lastly, if we have an x value that's between -3 and +2, we would use this function. So the first thing we need to do is find out what domain do each of these belong into. So -1 is not a value less than -3. It's not a value equal to -3, and it is a value that is between -3 and +2. Now, if it doesn't fall into any of those values, what we end up with is a undefined. So what we're going to use is our equation right here of 2x. So algebraically, this one's a pretty simple one, so we're not going to go crazy with it. But I could go to my graphing calculator and put in 2x, and we are looking up the value -1, and our value of -1 is also another output of -2. I should have probably looked at these. Every one of our answers has been -2 so far. Doesn't matter, but it's still just interesting. All right, let's take a look at another one of those. Evaluating a piecewise function. Try to get rid of this thing here. So we're evaluating a piecewise function for f of 0. So we look at our domains over there, and one of our domains is x values greater than or equal to 0, x values between, but greater than 0, not greater or equal to, greater than 0 and less than 5, and then greater than 5. So on this particular equation, the equal sign is the value that we're going to use. So the function that we have to use is our piecewise function that is at the beginning, which is the this equation right here. And what we do once we've decided which equation we're going to use is we then plug it in. Now this one we're not going to try to get too tricky with the thing. What we have is 0. When you plug in 0, 0 plus 3 would be 3, and then we square it, we would have 9. I'm going to take it to my graphing calculator again. You don't have to always use the graphing calculator, but it's a very useful tool. So I have negative x plus 3 squared plus 5. And I'm looking for an input value of 0. So when 0 goes in, hopefully you all can see this, negative 4 comes out. There we have it. All right, now we're getting into graphing a piecewise function. These can be very tricky. You're going to do a little bit of what I just did with you later. So just be prepared for that. I'm learning this thing and I don't know how to erase this efficiently, so we'll just leave it alone. Oh, clear all, that works. Okay, so this is how this is going to work. Notice this equation says we are going to use the negative 3x plus 9 for x values less than 1. And we are going to use negative x plus 14 for x values that are greater than 5. So it looks to me like we've got a big hole in our gap right here because we have no values between 1 and 5. That's not a problem. That's called a discontinuous function. So we can adjust and work from there. So let me just put these in right here. And I'm going to actually pull up a larger screen so that we can see it. Now I don't want both equations at one time. So I'm going to get rid of this. And the way I did that, I'll show you guys one more time, is I turned the equal sign off for the second equation, the negative x plus 14. So now it's not going to show up when I look at the table. So I need this for values less than 1. Well, the smart thing to do here is just to go to my graphing calculator and look up the value 1. Well, 1 is 6. That is the start, or technically it's the end of our graph, so it's going to be 1, 6. So the thing I've got to look at now is what kind of values am I going to use? This is a greater than or less than sign, excuse me, not equal to. So what we need to put here is an open circle. If I have an open circle, again that was 1, 6, so I'm going to start an open circle. I hope to. Right here. I'm going to show you how this works. I need another point, so another point that I have would be 0, 9. That would be there. Okay, now this goes forever to the left. I know this because I have a less than sign. So the way I turn this dot into an arrow is I click it once to get an open circle and I click it twice to get a straight line. So it's going infinitely in this direction. And our value of 1 does not have an equal sign, so this has to be an open circle. So this would look like this. This would be the first part of our piecewise function. It only goes for values less than 1. You see on the graph we have other parts over here like 4, negative 3, but that's not part of the domain of this function. Now I'm going to take a look at the second one. The second one picks up at the value 5. So I'm going to pull this up here for you. I don't need this one anymore because it's graphed, and I do need this one, so I swap the equal signs. And then I'm going to look at the table because I really don't care about the graph. And I was interested in the value of 5 and bigger. So you need to set the outer boundary. In this case, that outer boundary is 5. So I'm going to look at the x value for 5, and that is 9. So I'm going to go to my graph and plot the point 5, 9, which is right here. It also had a greater than sign, not equal to. So when I draw this line, I'm going to need to make sure that it is an open circle. So I go to 5, 9. That would be right here. I need another point on this graph. I wouldn't go too far. I like to go more than 1. But another point I see is 7, 7. So this is going through 5, 9. And since it's a straight line, it should follow the same slope over and over again. So 7, 7 is our point. Since it is greater than 5, I'm going to change this to a straight line. And since it has no equal sign, it is an open circle. So this would be the equation for the graph that we're looking at right there. Tables are really a good way to do these values. We just need to recognize the domain is when do we use a function and what function do we use. Let's do another one of those. Looks like I got 3 of these. We'll see if we need all 3. I may jump ahead on this. So let's take a look at this one. The other one has 3. Okay, this one is also very interesting. I added a radical in here. I think I gave you very few examples, but we haven't talked about radicals yet, but we can still see what they look like on a graph. And I'm matter of fact, I'm going to start with that one. So the square root sign is second, and then this value right here, and this would be. And this is what it looks like. So we can clearly see that this is the graph that we're looking for right there. Now, if you think about the transformations, this thing has just been shifted 4 units to the right, but I need to look at these values and see. Output value, because we only care about values of 4 or bigger. So this graph has got shifted over 4 units just like that. Okay, and it does go forever for values greater than 4. So this is actually what it looks like. Now, notice this. It says drag the blue arrow inward if necessary to set the domain. Well, our domain is only values that are greater than 4. I almost went too far. Make sure you don't do that. So we go there. But since it does not have an equal sign, I need to change this to an open circle, because negative 4, 0 is not part of the solution. So that's one piece of our piecewise function. I'm going to turn off the equal sign for that thing. And start the other one. Now the other one is for only for values, greater than 0 and less than 4. So when I graph this thing, I need to make sure that those are the values that I'm looking at. So there's my equation. I'm going to again go to the table. Table is our good friend. And we need the values 0 and we need the values 4. So there's 4 on the screen. And now 0 and 4 are both on the screen. This is a straight line. If you're not sure what you're looking at, just hit graph. You can see that this is definitely a straight line. So I'm going to go back to my table. And I'm going to plot the point 0, which is negative 4. So that would be 0, negative 4. That would be here. Oh, sorry. I need to go with a line here. And my slope was negative. So I had a point at 0, negative 4. And I had a point at 4, -8. And you can see that's going through 4, -8. So that's the right type of line. Now what I need to do is restrict its domain. Well, this thing only goes from 0 to 4. The 0 has an open circle because it does not have an equal sign. And the 4 has a closed circle because it does have an equal sign. So this is how we... Oh, I hit start over. See if that worked. It did not. All right, let me go quicker here. We had this one over at the 4. The domain was 4 over. It was a closed circle, open circle, excuse me. And then our second was a negative sloping line that crossed through -4. So it looked like this. It had a domain from 0 to 4 with an open circle at the 0 and a closed circle at the 4, but an open circle at the 0. Finish. There we go. Don't hit start over again. So this is what our function would look like. A lot of opportunities to make mistakes. Double check that you use the correct type of circles. That's where a lot of mistakes are actually going to take place, is on the use of circles, opened or closed. All right, so as we take a look at this one, you see we have another piecewise function. We're going to graph this piecewise function. It is a quadratic equation. You could graph this thing if you wanted to. It's just an x-intercept, x squared, a quadratic equation that's been shifted down 5 units. So let's just do that actually. We'll leave the calculator out of it. I am going to graph with the calculator just so we can see it again and reference the points that we end up with. So x squared minus 5. This is why transformations are good to get good at. Because you can take shortcuts. It's not really a shortcut, actually, poor choice of words, but you can get to the answers faster. So the other one, there's the absolute value. If you notice that, it was under math, and I'm going to put x minus 5 inside, and I'm going to put a plus 1 outside. And that one as well. It's a absolute value that's been shifted right 5 and up 1. So we'll do our transformations, but we'll get an idea of what these two look like. See, there's the quadratic and then the absolute value. We're obviously going to have to limit our domains, but that's what they should look like. So let's take a look at this thing. The quadratic function looks like this, but again has been shifted down 5 units, and it has not been manipulated in any other way. Just down 5. But the domain is only from -1, so we're going to pull this wall over to -1. And the other one has a wall at +3. So we set our walls just like that. Now it's a question of what kind of circles should we use. Well, at our -1 we do have an equal sign, which means it is a closed circle. That's already done. And our x value equal to 3 does not have an equal sign, so we need to have an open circle here. So this is what the quadratic equation, x squared minus 5, with a domain between -1 and +3 looks like. And then the second one is the absolute value family, so it's the V shape. We see that it has a x minus 5, which means the vertex is going to be shifted 5 units to the right. It has a +1, which means this is going to be shifted up 1. And then as you can see, as we're working through these, that's exactly what it looks like right here. If you needed to use the table to graph the points, go for it. So we're here. But this function is from values of 4 to infinity. So there will be no wall. We'll leave the arrow right there. Think about this as well. This is a greater than or equal to, which means it is a closed circle included in the data. So we're going to finish that up. We can take another brief look at this and see if everything kind of looks like it. Piecewise, I've heard people call these Frankenstein functions because it's just a piece here, just a piece there. So there's our Frankenstein function. couple of things we need to keep in mind. You can have an open circle. We don't have any overlap whatsoever, but you can ever have a line over a line or a dot, closed-in dot over a closed-in dot. We don't have any of those things, so this is at least a function, because remember, if it doesn't have that, it fails the vertical line test. And if it helps you, look at the piecewise that they put together, phase by phase by phase. And there we have our answer. And again, dots are going to burn you. Make sure you pay attention to the type of dots you're going to use. Okay, now for the really tough stuff. That is writing a piecewise function. Well, see, we have two parts here. Let's first talk about the domain. This function right here is coming in from negative infinity. They want me to write it in solution notation, so here's what we have. This will be x values less than or equal to -4. And think about why I use the equal to sign. And if you said, well, it's because it's a closed circle, you were exactly right. Now we have a domain for the second one. Well, we've got a big gap in here, and the next domain picks up at -1, and it's going to go infinitely to the right. So the x values will be greater than, but not equal to, -1. So there we have our domain. These are both linear functions. We're actually going to start with the second one because it's actually a little easier if you think about it. This is a y equals mx plus b. Well, the b value of this one is +3. So that's going to end with a +3. And remember, the m value is the slope, the rate of change. So what we're going to do is just simply count, rise over run. This is up 2 over 1. If you're not confident in your choice, you can always graph and see if it looks like what you intended for it to look like. So let's see, 2x plus 3. Obviously this has been cut, but yeah, that's what it looks like. And you can always check your domain. And you can see -1 does have an output of 1, check. 0 has an output of 3, check. Now for the second function, y equals mx plus b. Well, let's get m. Here's a point. We're going to rise 1, run 1, 2, 3, 4. So this is a slope of 1/4. Now for the y-intercept. Well, it doesn't cross the y-axis. Well, you got to ask yourself, if the line continued, where would it cross the x-axis? Y-axis, excuse me. So the slope is 1/4, so I'm going to count it again until I cross the y-axis. Rise 1, run 1, 2, 3, 4. So you can see that had this continued, it would have crossed at -1, which would have been its y-intercept. So its y-intercept would have been -1. I'm going to just make a real brief check to make sure I use the right type of circles. Values less than -4, closed circle, check. Values greater than -1, open circle, check. So this is writing a piecewise function. And we're going to up the ante one more time. Level 2 on this. And here we go. We've got 3 parts. So I'm going to have to add a rule. These are called rules. I'm going to first set the domain. X values less than or equal to. And then the first wall that we run into is -2. And I used an equal sign because that is a closed circle. Okay, the new pickup, rule number 2, the piece right here, picks up at -2 with an open circle. And it continues until it gets to 1 with a closed circle. So there's my second wall. It hit a wall here, hit a wall here, and then the last thing picks up where the other one left off. They don't have to do that, but this one does. And will go infinitely to the right. So those are all my domains. Wall 1, wall 2, wall 3. Okay, one thing I want to point out. Open circle over closed circle is okay. Closed circle over open circle is okay. Open over open would be okay. Closed over closed cannot happen because then it would fail the vertical line test, and you would not have a function. And you can't have a piecewise function if it's not even a function. Let's actually start with the middle one. Because we have the y-intercept, the y-intercept is -7. Y equals mx plus b, so all we need is the slope. We can see that this is going down 1 over 1, so the slope is just -1. We could denote that with just a negative sign. All right, now let's go over to the function right here, the equation right here. It looks like it has a slope of 1, rise 1, run, so that would just be 1x. We don't have to put 1x. And if we just continued this pattern, what would happen? Well, if it rose 1, it would run 1, still not on the y-intercept. If it rose 1, it would run 1, and it finally hits the y-intercept at 0. You technically wouldn't be wrong to say plus 0. I'm actually going to leave it like that to see if I'm telling the truth. But the y-intercept is the origin, so you don't have to put anything. And let's take a look at the last one. Any 2 points, by the way. So why not start here? The next place it touches is right here. This is a slope of rise 2, run 1. So the slope of this one would be positive 2x. Now the y-intercept. Well, we can't keep moving right because we're moving away from the y-intercept. So what we would do is undo the slope until we finally cross the y-intercept. So instead of going up to right 1, we're going to go down to 1, 2, left 1, which puts us on the y-axis, which means our y-intercept is -9. Now, hopefully I won't miss this because of the plus 0. I don't think I will, but we'll take a look. But our first thing I'm going to check, my circles. Is this a closed circle with an equal sign? Yes. Does this one start with an open circle on the left and end with a closed circle? Yes. And do we end with an open circle? Yes. You want to make sure you check those circles. It's very, very frustrating to miss because of the circles. And you see the plus 0 did not cost me. My answer still worked out. Completely unnecessary to put that, but it's not wrong to put it. So this was piecewise function. Tomorrow we will work on the section 1, and section 1 is easier because all we'll do is evaluate. We'll do some evaluations here. You see you have about a 5 here and a 5 there. That's just looking up the values. I tried not to give you too many on these, 3, 2, 2, and 1, 2 of those. I'm actually going to change that to 1 in a good mood. So we'll change that to a 1 right there. And this is your assignment. Good luck.